In the previous video, we solved an example with a block diagram for an LTI discrete time system, and we found that the relation between the input and the output was represented by this equation. And by the way, this equation is what we call the difference equation. This is what replaces the differential equation in the continuous time system. So instead of differential equations, we get something called difference equation. Difference equation where the output at different time instance, y of n, y of n minus 1, y n minus 2 in general, are related to the input at different time instance, x of n, x n minus 1, x n minus 2, and so on in general. So this is called the difference equation. From the difference equation, so from the block diagram, we obtain the difference equation. From the difference equation, when we substituted the input to be delta n, x of n to be delta n, the output will be the impulse response, h of n. We calculated the impulse response and we found that it is equal to delta at 0, another delta at 1, another delta at 2, with amplitude 1/3 for each of them. And this is what we call finite impulse response because it's finite, it appears only at few instances of time, few samples only, finite number of samples, so we call it finite impulse response. We'll see later that we have something called infinite impulse response where h of n is actually has infinite number of samples. So this is finite impulse response. So these are just definitions. The difference equation, this is an example of a difference equation, this is an example of a finite impulse response. Once we obtain h of n, the impulse response, I can ask you to calculate the output for any input. For example, let's take this example where I'm giving you the input to be, I'm giving you the input x of n to be 0, and then 0 here, and then at 1 it is 3, at 2 it is 4.5, at 3 it is 6, and then zeros. So this is an input, and I'm asking you to find the output given the same impulse response that we calculated. So we have a system with the same impulse response that we calculated previously, and this is the input we need to calculate that. So we know that the relation between the input output and the impulse response is the convolution, and we can write the convolution either summation of x of k h of n minus k, where you add over k from minus infinity to infinity. Our variable here is k, so you keep one of them as it is, and then you flip the other one and you shift by n, or you can write it as summation h of k x of n minus k for k equals minus infinity to infinity. So when we solve this example here, we are going to follow maybe this form. You can do the other one at home just to compare the answers. You should get the same answer exactly. So in this form, it says that the output at any instant n can be calculated by keeping h as it is, but we are going to change the axis name to k, and this is h of k. So h of k with k is the same as h of n with n, right? If I ask you to plot h of k with k, it is the same as h of n with n. It will be 3 delta functions, 1 3 over 3, 1 over 3, 1 over 3. And then the other one, remember that our variable is k here inside the summation. The other one is going to be reflected and shifted by n in general. So when you reflect this one, x of minus k, x of minus k with k will be something like this. Six, 4.5, and this is 3, right? This is x of minus k. And then when you shift by n, then x of n minus k will be, this is instead of minus 1, it will be n minus 1, n minus 2, n minus 3. So this is here, we are taking n equals 0, right? So when n equals 0, let's multiply. So y of 0, in order to get y of 0, you put n equals 0, right? And n equals 0, you are going to multiply h of k times x of minus k. You will find that the multiplication will be completely 0, right? 0, 0, 0. We are multiplying all these samples by zeros, all these samples by zeros. So you will get 0. Then, in order to calculate y1, you are going to shift x by 1 to the right? So x of 1 minus k, x of 1 minus k will appear as 3 here, 4.5 here, and 6 here. Right? So this is at 0, minus 1, minus 2. This is x of 1 minus, this is x of 1 minus k. Now let's multiply x of 1 minus k times h of k. Okay, so in order to get y of 1, we multiply x of 1 minus k times h of k. X of 1 minus k times h of k, you will find that the overlap is only in this sample. 1 over 3 times 3, it will give you 1. Next, in order to calculate y of 2, you are going to shift x one more sample, x of 2 minus k. So x of 2 minus k will appear as 3 here at 1, 4.5 here, and 6 here. Right? This is x of 2 minus k. Then, when you multiply h of k times x of 2 minus k, the overlap will be in these two samples, 0 and 1. 1/3 times 4.5 plus 1/3 times 3. So 1/3 times 4.5 plus 1/3 times 3. This will give you 1 plus 1.5 will give you 2.5. Next, in order to calculate y3, you are going to shift x by 3. You are going to shift x by 3. I'm going to remove this. You are going to shift x by 3. So, what you will get? You will get, if you shift x by 3, you will get here 6 here, you will get here 4.5, you will get here 3, 0, 1, 2, and then zeros. Now you multiply, this is x of 3 minus k, okay? You multiply h of k times x of 3 minus k, you will get 1/3, 1/3 multiplied here, 1/3 multiplied here. So it will be 1/3 multiplied by 6 plus 1/3 multiplied by 4.5 plus 1/3 multiplied by 3. This will give you 2 plus 1.5 plus 1. This is 4.5. Then, in order to calculate y4, you are going to shift one more time. You are going to shift x one more time. So it will appear as, if you shift one more time to the right, 6 will come here, 4.5 will come here, and 3 will come here. This is at 1, 2, 3, and this will be 0, 0, 0. This is x of 4 minus k. Now let's multiply x of 4 minus k times h of k. You'll find that the overlap will be only in these two samples, right? In 1 and 2. So it will be 1/3 times 6 plus 1/3 times 4.5. This will give you 2 plus 1.5, 3.5. And then we shift one more. We shift one more. So what we will get is, if we shift one more time, then here there will be 0 at 1. At 2, there will be the sample of 6. At 3, there will be the sample of 4.5. At 4, there will be the sample of 3. Then, when we multiply, this is x of 5 minus k. Okay? When we multiply x of 5 minus k times h of k, the overlap will be only in this sample. At 2, right? So it will be 1/3 times 6. So y of 5 will be 1/3 times 6 will be 2. Next, if you shift any more, if you shift x any more to get y of 6, for example, or y of 7, or y of 8, or any other y, if you shift x anymore, there will be no overlap, and the output will be 0. For all other shifts, the output will be 0. So the output now, we calculated the output for all the values of the shift, for all values of n, okay, and the result is this is the output y of n. We found that y of 0 was 0, and before 0 it was also 0 because there is no overlap. And then starting from 1, okay, it will be 1. At 2, y of 2 is 2.5. Y of 3 is 4.5. Y of 4 is 3.5. Y of 5 is 2. And then zeros after that. So this is the output of our system due to an input signal that was represented by x. This is the output of our system. So this is what we call the convolution in the discrete form. We did it by fixing one of the signals and we flipped the other one. We flipped the other one first and we kept shifting it to the right in order to cover all different shifts until there is no overlap between the two signals. We could have done the same solution without plotting by just using the table. For example, we can solve the same problem using a table without plotting the signals. So, I'm sorry I moved the signal. But anyways, we have the results there. I'm going to show you another method to solve the convolution. Well, so we can just make a table and write numbers. For example, we can make a table here and say this is instant minus, what was x? Okay, so x will appear up to minus 3. This is instant minus 4, minus 3, minus 2, 0, 1, 2, 3, 4. Okay, maybe up to we need up to maybe 5, huh? And then we are going to say this is the shift n and this is y of n. Okay, the result. So here in the first row you write what is h of n, what's h of k, what's h of k. So h of k with k, okay, this is 1/3 at 0, 1/3 at 0, 1/3 at k equals 1, so this is the k, by the way. H of k is 1/3 here, 1/3 at 1, and 1/3 at 2, and then zeros. X of minus k, x of n minus k. X of n minus k is going to be x of n minus k. We are going to flip the signal x, and let me remind you of the signal x. The signal x looked like this. Let me just put it here. The signal x looked like this. X of n, it was something like this. So it was 3, 4.5, 6. This is our signal x. So first, if we reflect it, x minus k with k, then you will get a sample at -1. Here, this should be -1, -2, and -3. So you are getting a sample at -1. It will be 3. A sample at -2, 4.5. A sample at -3, which is 6. And then zeros. This is x of minus k. Right? X of minus k, we can calculate منها. We can calculate y of 0, right? This is y of 0. We can calculate y of 0. Y of 0 equals what here? Y of 0 equals what? If you multiply h of k times x of minus k, you will find that the multiplication 0, 0, 0, 0, 0, 0. So the multiplication is going to be 0, right? And then x of 1 minus k. If we use n equals 1, n equals 1 means we are going to do a shift of 1, x of 1 minus k. We are going to shift x by 1 sample. So we are going to get 3 here, 4.5 here, 6 here, and zeros everywhere else, right? Then here, when we multiply x of 1 minus k times h of k, we'll find that there is only an overlap here. 1/3 times 3, which will be 1. So this is the second row. Then let's take n equals 2, which means that we are going to do a shift of 2. So this will be x of 2 minus k. X of 2 minus k, we are going to shift x by one more shift. So 3 will come here, 4.5 will come here, 6 here, and zeros. Okay, then we multiply x of 2 minus k times h of k. We'll find that we have overlap in these two columns. 3 multiplied by 1/3, 4.5 multiplied by 1/3. This will give you y of 2, which will be 1/3 multiplied by 4.5 plus 1/3 multiplied by 3. This will give you 1.5 plus 1, 2.5. And then you shift again, use n equals 3, and this will give you y of 3, okay? Then you will do one more shift, 3 will come here, 4.5 will come here, 6 will come here, and zeros everywhere else. Now the overlap will be in the 3 samples, 1/3 times 3, 1/3 times 4.5, 1/3 times 6. This will give you 4.5. You keep doing this, so if you shift again, if you take n equals 4, this will give you y of 4. And we shift again, 3 will come here, 4.5 here, 6 here, and zeros everywhere else. This will give you overlap only in these two samples, 1/3 multiplied by 4.5, 1/3 times 6 will give you 3.5. Finally, if you take n equals 5, this will give you y of 5, and we are going to shift one more shift, and zeros everywhere else. This is 0, okay? You will find that the overlap is only in this sample, 1/3 times 6, it will give you 2, right? Then if you shift any more, x of 6 minus k, if you take n equals 6, then you will find that 3 will come here, 4.5 here, 6 here. There will be no overlap. When you multiply x of 6 minus k times h of k, there will be no overlap between the samples, right? And the multiplication will be all zeros. All zeros, and the output will be 0. So here you find, or you see that we got exactly the same result, but we did the first solution using the plot, and the second solution using the table, and that was this example, and 2 methods to solve it. We'll see you in the next video with another example.